We'll be sorry. Hi everyone. We'll be starting in a few minutes. Oh, go ahead. So, anything else? Yes. Okay, this one. All right, how? This is change pieces. Good afternoon. Thank you for joining our CPD on thermal bridging. We're speaking from the kitchen in our offices in Guildford. My name's Anna. I'm one of the co-founders of SRE and the managing director.
My name's Elsa and I'm a building physics consultant specialising in energy and compliance.
And I'm Alicia. I'm also a building physics consultant specialising in environmental modelling. As we've had with our other CPDs, where a lot of people have been joining, we're aware that there's a huge range in the amount of technical detail people are wanting to take away from today. For those of you who like detail, there's quite a lot in here, and Hazel is going to be sending out a briefing note on thermal bridges in due course. For those of you who want less technical detail, I need to warn you, there's only so much talking about thermal bridging you can do without technical detail, as I've found out in the last few weeks. So bear with us. Finally, on this note, we are going to be referring to our notes a bit more in this CPD because of the nature of what we're talking about, and also because we're wanting to give you as much detail as possible. Thermal bridging is inevitable. There are always going to be breaks in a building's insulation at walls, doors, corners, balconies. However, as buildings are becoming more insulated, we are needing to make an even greater effort to ensure that heat loss through thermal bridging is minimised. Without doing that, a lot of the time and effort and cost that we're putting into insulating our buildings can be lost. The importance of thermal bridging is reflected in the 2021 Part L building regulations, which have not allowed accredited construction details for thermal bridging. They were deemed to be outdated and oversimplified. Thermal bridges now have to be modelled, or as we'll discuss later, an approved scheme can be used. For those of you dealing in commercial property, while accounting for thermal bridges isn't yet regulated, we recommend modelling and enhancing thermal bridging wherever possible, because if you do, obviously cooling and heating loads will be reduced. Also, on many of the schemes that we've worked on recently, particularly commercial, planners have asked for thermal bridging details for a number of walls, particularly partition walls between non-regulated and regulated space. Finally, it is worth noting that when we're talking about thermal bridging, heat can be transferred in both directions. In the UK, we usually talk about heat loss when we're referring to thermal bridging, but obviously in the hotter months in the summer, thermal bridging problems could lead to increased cooling load. We're going to start sharing our screen now. Elsa will start by looking at thermal bridges in relation to other types of heat loss, and we'll expand a bit on what we mean about thermal bridges. Alicia is going to introduce different types of thermal bridges, and I'll explain some of the implications of poorly designed thermal bridges. We'll outline how heat loss through thermal bridging is quantified and how we at SRE model it using our proper software, and how junctions and how we can determine how junctions are performing so we can make recommendations. We'll also explain how thermal bridging is modelled in SAP under Part L building regulations. Finally, we'll provide recommendations for minimising heat loss at 9 key junctions.
So heat can escape from a building, or indeed enter a building, in 3 ways: through the fabric, called fabric heat loss, through gaps or cracks in the fabric, so for example around poorly fitting doors or windows, called infiltration, or through mechanical or natural ventilation. When heat is lost through thermal bridging, this is via fabric heat loss. Thermal bridges, which some of you may know as cold bridges, are weak points in the building's envelope, where there's a significantly higher rate of heat transfer than the surrounding areas. Heat will always follow the path of least resistance, and thermal bridges therefore typically occur where there's a break in insulation, so for example at corners, around windows, or at the wall to roof junction, as you can see by the blue on this image, where there's a reduction in insulation, so for example around columns, or where the insulation is penetrated by a material with a higher thermal conductivity, which creates a bridge for the heat to pass out of the building, so where there are steel studs or joists within the insulation.
Heat can be lost through 2 types of thermal bridges, namely repeating thermal bridges and non-repeating thermal bridges. The image on the screen is an example of repeating thermal bridge, and it's a plan view of an external corner that we had modeled for one of our projects in Reading for ABRI. Here, the purple color depicts the areas with the lower heat transfer, while the white parts depicts areas with higher heat transfer. In this particular case, the metal studs forms the white parts because of its high thermal conductivities. In general, repeating thermal bridges are nothing but timber or metal studs in a framed construction like the image, or wall ties or mortar joist in a traditional construction. Essentially anything that interrupts the insulation at regular intervals. The repeating thermal bridges are accounted for in the U-value calculation, and so it does not require a separate thermal bridge calculation. On the contrary, non-repeating thermal bridges do not occur regularly throughout the fabric element. For example, like the ceiling, junctions, projecting balconies, eaves, etc. So the image is a plan view of a windowsill, where the window is directly sitting on the concrete slab, which is projecting to form a balcony. Here, the windowsill, along with the projected concrete slab and the metal stud connecting the wall buildup to the concrete slab, forms a thermal bridge, which is specific to a particular region or a length. The non-repeating thermal bridges are not taken into account in the U-value calculation, and so it has to be calculated through a separate thermal bridge calculation.
Thermal bridging will result in increased heat loss, and as buildings are becoming more insulated, as I mentioned at the beginning, a greater proportion of heat will escape through thermal bridges because they are always going to be the weakest point in the building envelope. To illustrate this, research has shown that buildings with high levels of insulation and air tightness can lose up to 30% of heat through thermal bridging. This can undermine the money and the work that's put into insulating a building, as well as increase the carbon emissions. Thermal bridging can also cause localized reductions in internal surface temperatures, which can lead to condensation. This can result in mold growth, for example, around windows, like we can see in the picture on the screen, or even interstitial condensation, which can build up within the partition walls, like I was explaining in the warehouses. But the problem is they can't be seen either from the kind of exterior or the interior. Mold growth can result in significant health issues, like we all know, asthma and other respiratory illnesses. Thermal bridging can be quantified in two different ways: psi values and FRSI values. Psi values quantify the thermal transmittance or heat loss, or indeed heat gain, through thermal bridging junction. The FRSI value, on the other hand, quantifies the surface temperature on the inside to assess the risk of condensation and of mold growth. At SRE, we use specialized software, which we've developed in-house over a number of years. The software takes into account the geometrical configuration of the junction, as well as the materials used and their relative conductivity.
The image you see on the screen is a sample case of a flat roof with parapet, which we have modeled using Therm software through the graphical user interface of Honeybee and Ladybug tools plugins within Rhino and Grasshopper. As Anna had already mentioned, we use the software that was developed in SRE because it is more flexible for the use and we can customize the outputs and the boundary conditions as required. And also we conduct regular quality checks against commercial thermal bridge softwares like Cypher. So when we look at how a thermal bridge is calculated, we first model the junction as accurately as possible, documenting all the materials, their correct thermal conductivities, the boundary conditions, etc. As per the BRE guide, we always follow an external temperature of 0 degrees Celsius and an internal temperature of 20 degrees Celsius to represent a worst case scenario. It has to be noted that thermal bridge calculation is very sensitive, and so incorporating all those minute details with the correct materials and conductivities is imperative. We also use the Therm software to create different outputs like thermal plan, heat flux plan, dew point plans, etc. For the ease, we are showing an image of a thermal plan on the screen, as it gives you an idea of the heat flow across the junction and also gives you all the necessary information related to the thermal bridge calculation. Here, as in the legend, the red denotes warm and blue denotes cold. It also demonstrates the point of minimum surface temperature as well. Once here, the point of minimum surface temperature is right below the steel stud, connecting the two timber joists together as represented. And as once we have calculated the thermal bridge, it is easier for us to identify the region where the heat loss is happening and recommend solutions. In this particular case, adding a thermal brake pad beneath the steel fixings can be a potential recommendation to reduce the heat loss through this particular junction. In SRE, we also, our software also helps us to predict the risk of condensation through FRSI value calculation. And BRE suggests an FRSI value of minimum 0.75. It has to be noted that this calculation is purely temperature based and does not take into account any vapor pressure distribution or membranes as such. Now, Elsa will talk more about the role of thermal bridges in SAP.
Thanks, Alicia. So in SAP assessments, the total fabric heat loss is made up of element losses and thermal bridge losses. So element losses are calculated in U values, and as Alicia mentioned earlier, account for any repeating thermal bridges, so your steel studs, wall ties, and these typically account for 70 to 80% of the total fabric heat loss. Thermal bridge losses are calculated by multiplying the psi value of a junction by its length. And this means that junctions with a high psi value, or that occur over significant lengths, have the highest impact on heat loss from thermal bridging, and hence the SAP results. So as most of you are probably aware, the 2021 version of building regulations Part L, changed how thermal bridges are assessed. Previously, accredited construction details, or ACDs, could be and were used for the majority of junctions. These were standardised details developed in 2002. However, as Anna's mentioned, they're now considered to be outdated and can no longer be used under Building Regulations 2021. Instead, junctions can either follow a reputable non-government database, and there's a range of schemes available for a range of different construction types, or they can be independently calculated following the guidance in the second edition of BR 497 2016. However, please note that there are a few schemes such as LABC and CBA, which were calculated under an old version of BR 497 and so can't be used in the current building regulations. There are a lot of junctions in dwellings, however, not all of them necessarily need to be assessed to pass the SAP requirements. And for some junctions, worst case default SI values can be used, particularly if these junctions only occur over short lengths. Another change under the Building Regulations 2021 is that photographic evidence is now required for key junctions. And these photos need to be taken during the construction process when the junctions are still exposed. Anyone can take the photos, they just need to be date stamped and geolocated. And there's a range of apps available, such as SiteMate or SiteWitness, that can assist in taking and organising these photos.
These junctions represented here as sample cases are the ones we have modelled for PMC construction for their latest residential development in Portsmouth. These construction details are steel construction details, but similar principles can be applied over other construction types as well. As a general practice, we should always try to make the insulation as continuous as possible and avoid direct contact between two materials of higher thermal conductivity. There is a general notion that having an improved U value reduces the heat loss to thermal bridges. But in practice, it actually increases the heat loss to thermal bridges as heat tries to escape through the easiest path with least resistance. Hence, you have to find a correct balance between the two. The recommendations that we are going to suggest further are beneficial to reduce the heat flow through junctions, but it has to be noted that each junction is unique, and so the approach might differ and there is no one universal solution. In general, the junctions related to window frames or door frames are harder to meet the SAP notional psi value. And here we are going to recommend a few tips and tricks that will help to reduce the heat flow through the window, door, and jamb. First would be, the first recommendation include insulating the reveals or gaps using PU form as depicted on the screen, maintaining a minimum overlap of 30 to 50 mm between the frame and insulation, avoid direct contact between steel fixings and the window frame, use low thermal conductivity cavity closures using materials such as PIR insulation, and if you're going for a traditional construction, go for a lightweight inner block work with low thermal conductivity if it is feasible. The next junction would be lintel junction. In addition to the recommendations that we had mentioned for the overlaps, reveals, and cavity closures, we should always insulate behind the metal flashing as highlighted using PU foam or materials with similar thermal conductivities. We should add thermal brake pads to avoid direct contact between steel fixing. And if we are opting for a steel lintel, we should always opt for a thermally broken one.
So for window or door sills, in addition to the jamb and lintel recommendations that Alicia mentioned, such as the 30 to 50 millimeter frame overlap, having a low thermal conductivity cavity closure and PU foam, we have a few more recommendations for sills. So when connecting the steel fixings to a component with a higher thermal conductivity, like a concrete slab, we would recommend using a thermal brake pad or even just plasterboard between these two materials. We would also recommend firmly braking the door frame where it's fixed to the slab. So for example, in one project, we assessed a door sitting directly on a concrete upstand which resulted in a bridge through the upstand to the ground. We proposed replacing this upstand with a thermal coursing block or adding an insulated strip pad, which significantly reduced the heat transfer and the psi value. For ground floor junctions, experience has shown us that well-designed junctions for ground floors are extremely important, as these junctions can occur over significant lengths. Our recommendations would be using low thermal conductivity blockwork, if feasible, or even just localised around the ground floor junction, using edge or perimeter insulation, which we'd recommend has a minimum thickness of 50 millimetres. And if there is a service void, extending this edge insulation into the service void between the plasterboard and the blockwork can help reduce the psi value further. Where possible, using a thermal coursing blockwork instead of a concrete upstand if this is feasible, or opting for a suspended slab foundation rather than a raft slab foundation, as this way the wall insulation continues below the damp-proof coursing, reducing the heat loss and the psi value.
So for balconies, the SAP team would recommend firstly avoiding breaking the insulation through projecting the floor slab out to form a balcony. Instead, they would advise using bolted steel balconies or self-standing steel balconies wherever possible. If those aren't possible, they would suggest adding a thermal break where we've shown in the diagram. And to further reduce heat transfer, underfloor insulation could be added internally, again, as we've shown on the diagram, but we would recommend a minimum of 1 metre near the junction to make it meaningful. Similar to ground floor junctions, roof junctions can significantly impact a SAP assessment. One of the top tips from the SAP assessors would be to avoid continuing the roof slab to form a parapet and always add some form of thermal break or consider structurally stable alternative parapet options. However, if these are unavoidable, whilst designing a flat roof with a parapet, we would recommend extending the wall insulation to the edge of the concrete parapet and providing edge insulation, or adding insulation below the terrace floor, covering again a minimum of 1 metre in length. You could also consider using under slab insulation, again a minimum of 1 metre in length, or wrapping corners under slab insulation.
In terms of roof junctions, the insulation can be applied at the rafter level or ceiling level. Here, we are going to discuss our recommendations for our roof junctions when the insulation is at rafter level. We should always have a continuous insulation. That is, the rafter insulation should meet the wall insulation without any interruptions, such as wall plates, patterns, etc., as highlighted in yellow. Similarly, adding insulation behind the plasterboard or over the service void as highlighted in red can be beneficial in reducing the heat loss through these junctions. In one of our projects in Hounslow, we had applied these recommendations and the junction was able to attain the SAP notional psi value.
So again, with roofs that are insulated at joist level, you want to focus on the continuity of insulation. And we would also recommend adding additional rafter insulation, again at that minimum of 1 metre in length. For inverted eave junctions, we would suggest adding edge insulation externally and trying to ensure continuity of the edge insulation with the roof insulation. Another option would be adding horizontal strip insulation below the slab, again at a minimum of 1 metre of length.
Great, thank you. That is the end of the presentation part of the CPD. Please do unmute yourselves and ask questions if you have any questions. We're here. I don't think, have we had any questions in the chat? We haven't had any questions in the chat. You must have questions on thermal bridging. Does everyone have capability to put questions in the chat if they want to do that? I know there's a lot of people on today's CPD. Elsa, do you want to answer the question? What are the reputable non-government databases?
So there's quite a few databases out there. We do have a list that's been provided by our SAP software with all the sources available. So if you want us to check them, we can check it through for you. But yeah, the key ones that we've used are the recognised construction details, have a lot for masonry construction, and then GRE have quite a few on their website for a range of steel frame, timber, masonry. So there's a lot out there. You just have to be careful that it's that they're using the current version of BR 497 and not the old version pre-2016.
Thanks, Elsa. Any more questions? Either, unmuting. Do all the detail described need to be anyway calculated and confirm the accredited software? Elsa,
So
Anna?
we not all of the details need to be assessed to pass the SAP requirements. So we kind of focus on doing the key junctions. So generally around 9 key junctions. That will depend on the dwelling. Some dwellings need more junctions calculated. So we focus on the ones that kind of have a significant length. So your ground floors, your roofs, your corners. And then maybe some, if there are some junctions that you're concerned about, that they might have condensation risk, we can also calculate them. But yeah, not all of them need to be calculated to pass that.
In addition to that, we do calculate the junctions when when it's not following the traditional way of construction. So if you are following the traditional or like recognized details, you wouldn't need to calculate the thermal bridges.
That's good. Does that help? Does that answer your question? We'll move on to the next question. Should the use of PU foam be advised given the fire implications? Alicia?
So the PU foam, I had a feeling that this question might be coming up. So for high-rise buildings, there are fire-related issues, and so PU foam is generally not advised. In such situations, you can maybe go for any aerogel products because they are fire-rated, I believe, and has good low thermal conductivities, or any other products, or I would say packer materials, or maybe insulated plasterboards too, which are fire-rated to replace the PU foam.
Thank you, Alicia. Do you do similar calculations where lower embodied carbon is considered? Elsa?
Yeah, so the psi value calculations themselves don't take into account the embodied carbon. They're just looking at the heat loss through the junction. It would be a separate kind of whole life carbon assessment that will be needed to look at the embodied carbon. And we've done comparisons before. I think Alicia did one recently where we compared U values for a range of different. Well, we compared, I think, roof build up for a range of different construction types and looked at the heat loss and the embodied carbon implication of the two.
Thank you. This is the question on how we charge. Do we charge for each psi value for a SAP? How do we do that?
Yeah, so we do charge for each psi values, but generally when a project comes in, it usually have like 2 or 3 or up to 10 psi values had to be calculated for a single project. So yeah, generally as a best, we do charge for one bridge at a time. Yeah.
And Alan, in answer to your question, will the slides be circulated after the meeting? This session is being recorded and it's going to be put on YouTube, and Hazel, who's here, will be sending out a link either this afternoon or tomorrow morning. So you'll be able to do that. If you specifically want the presentation, then just email Hazel at sre.co.uk and she can send it to you. Another question, what are options for reducing cold bridging on steelwork connections where they pass through cladding at eaves or the parapets?
The obvious answer would be to add thermal brake pads because they are load bearing, and if you are choosing structural thermal brake pads, they have the same load bearing capacity as a structural steel plate. So thermal brake pad would be an option. Then you could also go for foam glass products or foam, I would say foam boards, which have compressible strength, good compressive strength. And We don't specify products here, but there are products available in the market which can be used in such situations where you require some load bearing capacity and also prevent the thermal bridge. If you're going for lintel in a steel construction, there are a lot of thermally broken steel lintels available. And yes, parapets, if keeping a window frame on a parapet is unavoidable, maybe we can use like a thermal break pad strip just below the frame to avoid any heat loss through those junctions.
I hope that helps, Jonathan. Let us know if you want more information. And Natalie, is there an alternative method, can't use a shop product, of mitigating thermal bridging to balconies? I know that's something we gave a couple of recommendations, but
I didn't quite understand the question.
Is there an alternative method of mitigating thermal bridging to balconies if you can't use the shop product?
Since each balcony junctions, in general, all junctions are unique. So if we can see the actual junction, the drawing, it would be easier for us to suggest recommendations, because we always try to avoid placing the window frame on the RCC, or concrete slab as on its own, because it creates a large thermal bridge across it. So it is always advisable, if you can send us the detail, we can have a look and give you our suggestions and recommendations.
That's great. Thanks, Alicia. That's really helpful. And Andrew has asked, once a SI value has been calculated on one project, can this be used again on future projects? We are working with a number of our clients that we've worked with for a long time who use similar building methods and similar ways of construction, for example, Sterling property. And so, yes, we are doing that. We're meeting with them and helping. But do you want to explain a bit more about that, Elsa?
Yeah, so so you can use them again, essentially, as long as it's got the same construction. You could, if you changed like a small thing about the junction, so the insulation type. I believe that's something we can amend in a calculation. But yeah, as long as you're it's following the same junction detail, you can then use it on any future project. It's the same as kind of using one of those ones from the scheme. They can be used for multiple projects as long as you're just following the principles.
And for SI calculations, can you review project information to assess the number of junctions requiring assessment? And would you expect the architect to identify these? This is what we do when we're pricing jobs. Yeah,
so generally we kind of start off and look at the project and kind of identify what we think are the key ones, and start off by calculating those ones. Sometimes we find that we need to do a few more if it's still not passing the SAP requirements, because particularly under the new regs, it can be quite hard to get them across the line. But yeah, so sometimes the architects come to us with the details they want us to model, and sometimes we go to them. So it's a bit of a two-way thing.
And also, in addition to that, when identifying the bridge that you need to calculate, it's always the ones that are repeating throughout the development, or the one that covers a larger length across the development.
Yeah, so it's typically the same ones. It's often like the window junctions, your ground floor junction, your roof junction, your corners. Those are the ones we start off with, and then sometimes we need to do a few more.
I hope that helps, Alan. Any more questions? Either again unmuting yourselves or adding them to the chat. No more questions. There's only so much you can talk about on thermal bridging, I think. Thanks, Hazel. So thank you so much. We're going to draw it to a close. This was the fourth presentation in our current series of 4. I think many of you have watched a number of them. So I just thank you for that. And I'm sorry for any of you if you couldn't join the last one. We actually exceeded our Zoom capacity for attendees, which we have obviously listed now, but we didn't know was possible at the time. Thank you for taking the time to watch, and please do give us feedback. We love feedback. And on that, we are planning another series because of the feedback we've had on this, another series of 4 CPDs in the autumn. We're going to be looking at the new version of BREEAM, which is due out any minute, version 7. We're going to be looking at life cycle costing, and we're also going to be looking at TM54, which looks into operational energy, which is something we're using increasingly on a lot of our existing buildings at the moment. That's it from Elsa, Alicia, Hazel and myself. Thank you and goodbye.
Thank you.
Thank
Bye.
you.